Welcome to my 67th tutoring session in A-level chemistry. In this video, I'll explain the atomic orbital, molecular orbital, bonding orbital, and antibonding orbital. Atom is the smallest unit of an element. It has a central nucleus that contains positively charged proton and electrically neutral neutron, with negatively charged electron orbiting around the nucleus in its respective shell or energy level. I have color coded the subatomic particles. Proton is positively charged, neutron is electrically neutral, and electron is negatively charged. The nucleus of hydrogen atom, it contains only one positively charged proton and only one negatively charged electron orbiting around the nucleus in its respective shell or energy level. Now the electron is present in the first shell, which is also the outermost valence shell of the hydrogen atom. Hydrogen is the first element in the periodic table, and it is the only element without a neutron. The only electron that is present in the outermost valence shell or the first energy level, that is orbiting around the nucleus, is present in the 1s orbital. The first electron that occupies the orbital is always assigned a spin value of +12, and the second electron that is occupying the orbital is assigned a spin value of -12. And the spin of these electrons is denoted by up and down arrow. The spin of the first electron that is occupying the electron is denoted by the up arrow, while the second electron that is occupying the orbital is denoted by down arrow. Now hydrogen atom is represented by symbol H followed by a dot, where H represents the hydrogen atom, the symbol, while the dot represents the electron that is present in the first energy level or the outermost valence shell of hydrogen atom. Now hydrogen is not present in the atomic form. In fact, it is present in the molecular form as a diatomic molecule, and it is found by mutual sharing of electrons between the hydrogen atoms involved in bond formation. Now each hydrogen atom has a half-filled s orbital, and the bonding molecular orbitals in case of hydrogen molecule is formed by the combination of the half-filled s orbitals of these two respective hydrogen atoms. And the spin of these two electrons that is shared by the two hydrogen atoms is represented by up and down arrow. Now where is the electron in an atom actually present? It is present in the shells or energy levels. And where in the shells? In the shells, it is present in the subshells. And in the subshells, they are present in the orbitals. So the final destination of electron is the orbitals. And it is the orbitals where the electrons are housed. There are 4 types of orbitals: s orbital, p orbital, d and f orbital. There is 1 s orbital, 3 p orbitals, 5 d orbitals, and 7 f orbitals. Electronic configuration of hydrogen is 1s1. The electronic configuration is written as sequence of numbers and letters, with number representing the energy level, letter representing the orbital, and the superscript number representing the number of electrons present in that particular subshell or orbital. And hence the electronic configuration of hydrogen is 1s1. and the spin of this odd electron in the hydrogen atom is denoted by up arrow. So electronic structure of hydrogen atom, it has a nucleus with only one positively charged proton and negatively charged electron orbiting around the nucleus in the 1s orbital. And in case of carbon, two electrons present in the 1s orbital in the first energy level, and in the second energy level, that is in the L shell, two electrons are present in the 2s orbital, while the remaining two electrons are present in the p orbitals. One electron is present in the 2px orbital, one electron in the 2py orbital, while the 2pz orbital of the carbon atom is vacant or empty. So 1s2, because two electrons are present in the 1s orbital, 2s2, because two electrons are present in the 2s orbital in the second energy level, and 2p2, because two electrons are present in the 2p orbitals in the second energy level. And hence the electronic configuration of carbon is 1s2, 2s2, 2p2. While in case of sodium, two electrons are present in the 1s orbital in the first energy level, two electrons are present in the 2s orbital in the second energy level, six electrons are present in the 2p orbitals in the second energy level, and in the third energy level of the sodium atom, there is only one electron present in the 3s orbital, while the 3p and 3d orbitals are vacant. 1s2, because two electrons are present in the 1s orbital, 2s2 and 2p6, because two electrons are present in the 2s orbital, and six electrons are present in the 2p orbital, the second energy level. 3s1, because there is only one electron present in the 3s orbital in the third energy level or the third shell. And hence the electronic configuration of sodium is 1s2, 2s2, 2p6, 3s1. So 2n square is the general formula used to mention the maximum number of electrons present in each shell, or the number of electrons that can be accommodated by each energy level. So electronic configuration of sodium is 1s2, 2s2, 2p6, 3s1. And as you can see, the distribution of electrons is denoted by up and down arrow. The first electron that occupies the orbital is denoted by up arrow, while the second electron occupying the orbital is denoted by down arrow. And in the third energy level, or in third shell, you can find that there is only one electron present in the 3s orbital, and hence it is denoted by up arrow. Now in the hydrogen atom, the only electron in the outermost valence shell is present in the 1s orbital, and hence the hydrogen atom is half filled. What is an atomic orbital? Now atomic orbital is a three-dimensional space or a region around the nucleus of an atom where the probability of finding electron is more. So in case of hydrogen atom, the probability of finding electron is more in case of, in the 1s orbital. And there are four types of atomic orbitals, and these atomic orbitals are classified based on their shapes. S orbital is spherically symmetrical shape, example 1s and 2s orbital. P orbital is dumbbell shaped, example 2p, 3p, 4p, so on. D orbital is bit complex, it is double dumbbell shape or butterfly shape, while the F orbital with a much more complex shape, example will be 4f, 5f and 6f orbitals. Now hydrogen atom has a single electron in a 1s atomic orbital, while carbon atom has total of 6 electrons present in the 1s, 2s and 2p atomic orbitals. Now talking about the shape of orbitals. Now why s orbital is spherically symmetrical and represented by a sphere or a circle? The reason is the density plot of 1s orbital with one electron in hydrogen atom is distributed in the shape of a circle. So the probability of finding the electron in hydrogen atom in this spherical area is more in case of hydrogen atom. And hence the spherical or symmetrical shape is assigned for the 1s orbital for hydrogen atom. So based on the probability of finding the electron in the spherical area, the orbital shape is assigned as spherical or symmetrical. Now, while in case of p orbital, there is equal probability of this electron to be present either in the upper lobe of p orbital or the lower lobe of p orbital. And the probability of finding this odd electron is in the dumbbell shaped area. So the probability of finding the electron in this dumbbell shaped area or in the figure 8 shape is more. And hence the dumbbell shape is given for the p orbital. And the probability of finding the p electron is 0 in the nodal region. So here's the density plot of 2p orbital with 1 electron. So whether the p orbital is filled with 1 electron, odd electron, or whether it is completely filled with 2 electrons, the probability of finding the electrons is more in the dumbbell shaped area. And hence the dumbbell shaped is assigned for the orbital, p orbital. Now for the formation of hydrogen molecule, there should be interaction between the 1s atomic orbitals between these two hydrogen atoms. 1s atomic orbital of one hydrogen atom interacts with 1s atomic orbital of another hydrogen atom. Now what is a molecular orbital and how it is formed? A molecular orbital is formed when atomic orbitals of two atoms combine in a molecule. So the atomic orbitals combine to form molecular orbitals in molecules. Like in case of hydrogen molecule, you find that a molecular orbital is formed when the atomic orbitals of two hydrogen atoms combine, resulting in formation of hydrogen molecule. Now during the interaction, there are some requirements. Only when these requirements are met with, it brings about interaction between these atomic orbitals. So what are the requirements? So in order for the atomic orbitals to interact, they should be of same size, same symmetry, same energy, and moreover they should be half filled. Only when these requirements are met with, you can expect the atomic orbitals to interact with each other. And after the interaction, it results in formation of molecular orbital. So what you see here is a combination of or combining of half-filled s orbitals of hydrogen atom, resulting in formation of bonding molecular orbitals. So there are two types of molecular orbitals. One is bonding molecular orbital and the other is the anti-bonding molecular orbital. So when two hydrogen atoms combine, their molecular orbitals form a bonding molecular orbital as well as an anti-bonding molecular orbital. So as I already mentioned, the two atomic orbitals of hydrogen atom interact to form molecular orbitals if and only if they are of same energy, size and symmetry. Now in case of bonding molecular orbital, it is also called as HOMO, that is highest occupied molecular orbital. You find a region of high electron density between the nucleus of two atoms. So in case of bonding molecular orbital, it is the attraction between the positively charged protons in the nucleus and the shared pair of bonding electrons that holds the molecular orbital together in a stable form. Well, in case of antibonding molecular orbital, it's also called as LUMO, that is lowest unoccupied molecular orbital, you find a region of zero electron density between the nucleus of two atoms. And this leads to a repulsion between the nucleus, making the molecule highly unstable. Now talking about the labeling of the molecular orbitals. Now molecular orbitals are labeled with Greek letters like sigma instead of S and pi instead of P. And this is done in order to distinguish them from from their atomic orbitals, just to avoid the confusion. So sigma instead of S and pi instead of P. Now the concept of molecular orbitals explains the bonding in diatomic molecules like hydrogen, oxygen and nitrogen using the molecular orbital theory. So combination of S bonding orbitals of hydrogen to form bonding molecular orbitals. So this leads to formation of two types of molecular orbitals. One is bonding molecular orbital, other is the antibonding molecular orbital. So the bonding molecular orbital is lower in energy, and this lowering of energy is because of a region of high electron density that is seen between the nucleus of two atoms. And as a result, there is effective attraction between the nucleus and shared pair of bonding electrons of opposite spins, making it more stable and lower in energy. While in case of antibonding molecular orbital, it is high in energy as there is a region of zero electron density between the nucleus of two atoms, which leads to enormous repulsion between the nucleus of both the atoms, as the nucleus is positively charged, and since they are exposed to each other, it leads to repulsion between the nucleus. A bonding molecular orbital is formed when half-filled atomic orbitals combine constructively, that is in phase. Now the molecular orbital is a covalent bond, and like an atomic orbital, a molecular orbital can accommodate only two electrons. As you can see in the hydrogen molecule, you can find two electrons between the nucleus of the two hydrogen atoms. So a molecular orbital can accommodate only two electrons. So what are the major properties of a bonding molecular orbital? So it is lower in energy than the corresponding atomic orbitals, increased electron density between the nuclei, and moreover, the electrons in the bonding molecular orbital should have opposite spins. And this leads to bond formation and molecular stability. So in hydrogen molecule, two 1s atomic orbitals combine to form a bonding orbital as well as antibonding molecular orbital. The most important thing to note here is that the bonding orbital is filled first, creating a stable hydrogen molecule. And this is followed by the antibonding molecular orbital. So the bonding orbital is filled first, creating a stable hydrogen molecule. Now the antibonding orbital in the ground state, it remains empty, and only on excitation it causes transition to the antibonding molecular orbital. So antibonding molecular orbital is formed when atomic orbitals combine destructively, that is out of phase. And hence the antibonding orbital is higher in energy than atomic orbitals. This is due to reduced electron density between the nuclei, as the nuclei of the respective hydrogen atoms are directly exposed to each other. And this destabilizes the molecule if occupied by electrons. And that's about the bonding and antibonding molecular orbital in case of sigma bond. And let's try and understand the formation of bonding and antibonding orbitals in case of pi bond. And let's consider ethylene as a representative example. Now remember, A pi bond formation is always associated with formation of a sigma bond. Now sigma and pi bonds are perpendicular to each other. In contrast to the sigma orbital, the pi molecular orbital has zero electron density along the molecular axis, but has maximum electron density above and below the internuclear plane. And that is why the sigma bonds and pi bonds are perpendicular to each other. Because the pi bonds, they are formed by overlapping of p orbitals by sidewise or parallel overlapping. So pi bonds are formed by overlapping of p orbitals on adjacent carbon atoms, and this occurs by sidewise or parallel overlapping of p orbitals with a nodal plane at the center, separating the upper and the lower lobes of the p orbitals. And this results in formation of a pi bond. I have color coded the pi bond and the sigma bond. Pi bond is colored in purple color while the sigma bond is colored in yellow. This is to differentiate these two bonds. So pi bond, as we have seen in this diagram, it is formed by overlapping of p orbitals by sideways or parallel overlapping with a nodal plane in between. And what about the sigma bond? Now sigma bond is formed by overlapping of sp2 orbitals of the carbon atom, and this occurs by endwise or linear overlapping. So sigma bonds, they are formed by overlapping along the internuclear axis, and these are called as sigma bonds. And this is why the sigma bonds and pi bonds are perpendicular to each other. The reason being, a pi bond is formed by sidewise or parallel overlapping of p orbitals, while the sigma bond is formed by endwise or linear overlapping of the sp2 orbitals of the adjacent carbon atoms. So a pi bond formation is always associated with formation of a sigma bond. And that is how the ethylene molecule is formed. Now talking about the bonding and antibonding orbital formation in case of ethylene molecule. Now the ground state of pi electrons in the bonding orbital is represented by symbol pi, while the excited state of the pi electrons in the antibonding orbital is represented by pi star. On photoexcitation or on exposure to the UV visible radiation, pi electrons in the ground state undergo transition or get excited to the antibonding orbital state. Now the electrons are paired in the ground state, that is in the bonding pi orbital. On photoexcitation, you see the excited state of the pi electron in the antibonding pi orbital, that is mentioned by pi star. So in ethylene molecule, pi bonds are formed by overlapping of p orbitals perpendicular to the internuclear axis, and hence are called pi bonds. At the nodal region, there is zero electron density. So the probability of finding electron in the nodal region is 0. I have color coded the ground state and the excited state of pi electrons. The bonding pi molecule is represented in purple color, while the antibonding pi molecular orbital in the excited state is highlighted in red. So radiation in the UV visible region is absorbed through excitation of electrons involved in the bonds between the atoms making up the molecule. So the electron cloud holding the atoms together redistributes itself and the orbitals occupied by the bonding orbitals no longer overlap. Here's one more figure representing the bonding and antibonding pi orbitals of ethylene. Now in the ground state, you can see that the p atomic orbital on carbon atom and the p atomic orbital on the carbon atom B, they overlap with each other, and this results in formation of bonding pi orbitals in case of ethylene. This is in the ground state. This is by effective overlapping of the p orbitals on adjacent carbon atoms A and B. So the orbital resulting from the in-plane combination of atomic orbitals has a region of relatively high electron density between the two nuclei. Now this electron density attracts the positively charged nuclei and keeps them together. And for this reason, this orbital is known as bonding orbital. The other orbital has decreased electron density between the nuclei. This means that the two positive charges are not shielded from each other, and so they experience a repulsive force. This orbital is therefore known as the antibonding orbital and is of higher energy or of less stability than the bonding orbital. Thank you so much for watching my video. I hope you enjoyed it, and I'll meet you in my next interesting tutoring session.